Assuming that you understand the intuition behind polymorphism versus dynamic binding, we're now going to make things a little bit more formal and precise. And let me set the context to you first. We talk about inheritance hierarchy. So far, the hierarchy we talk about is very simple. Under the students, we only got one layer of the resident students versus non-resident students. But in general, we can expand the layers to as many, as deep as we possibly need. In that case, for example, we can expand the student hierarchy to be, let's say under students, we have either domestic versus foreign. And under domestic, we can have either domestic resident students with some premium rates versus we can get domestic non-resident students with some discount rate. And symmetrically, we can say under foreign students, we can either have foreign residents versus foreign non-resident, and etc. So how many layers you really want to, how deep you really want your inheritance hierarchy tree to be is completely up to you, up to the need of your application. Let me just go over another hierarchy over here for the smartphones. So this will be the more complicated running example I would like to go through together with you as we introduce more complicated concepts about typecasting and also some other polymorphism and dynamic binding example. Okay, let me switch to my iPad, but you can also get access to this diagram here from the lectures website. So you can download this PDF. So this is the inheritance hierarchy over here. I would suggest maybe after you walk through together with me about the basic features for every layer, for every level of classes, you can maybe pause the video and try to study a little bit about the intuition behind this inheritance hierarchy before you move on. Okay, so I'll let you download the diagram and study a bit yourself. Okay, let me switch to my iPad and then talk about the features very quickly. So now we basically have the top level, we have smartphone. Okay, so that's a smartphone. That's the kind of the top level concept that we want to define. And then under the smartphone, we can either get iOS or we can get Android. So that's the first level. And under iOS, we can either get iPhone XS Max and also or we can get iPhone 11 Pro. I'm not being very up to date for the latest Apple events, but we'll live with this example here. And then also under Android, we got let me just get another color here. Let's say we got either Huawei or we got Samsung. And under Huawei, it can either be P30 Pro or it can be Mate 20 Pro. Under Samsung, it can be Galaxy S10 and also Galaxy S10 Plus, etc. So you can see the idea over here. So we got different branches. Under different branches, we might introduce more features unique to that particular branch. So that's exactly what you can do when you introduce new subclasses. So let's just go over some basic features here. You can see for smartphone, all we require for each smartphone to satisfy either iOS or Android will be you must be able to dial. And also you must be able to surf the web. So these are the two most basic features you want to support for every smartphone. What about for iOS? For every iOS, number one, you will have some new feature called FaceTime. Let's say the FaceTime is only unique to the iOS. And then for Android, let's say the only feature that's unique would be called Skype, for example, right? So Skype is not really available in iOS, and FaceTime is not really available in Android, let's say. And then what about redefined features? You can see the surf web is already here, but now let's say when you are talking about iOS, you may redefine the surf web to be using Safari. So let's say that that's the default web browser by the iOS. And then what about the surf web to be redefined in the context of Android? Let's say we do use the Firefox web browser for Android by default. Okay, let's go a little deeper here. Let's say for iPhone 11 Pro, let's say for this kind of phone, they have a very unique feature called Quick Take. So I believe it's just to take the pictures more quickly, literally. That's its literal meaning. Okay, and then for Huawei, under this particular model P30 Pro, they also have another unique feature here called Zoomage. I think that one has to do with using some AI to really support the function. Okay, you can look it up on the web if you wish. And then also for Samsung, let's say every Samsung phone also have this particular feature that's unique called Side Sync. Okay, so you can imagine that for Galaxy S10 and also for Galaxy S10 Plus, both of them will actually support side sync. Okay, and then for Huawei, if you only talk about generic phone for Huawei, it may not necessarily support zoomage. It's only available for this particular model. And if you talk about this model here, it does not support the zoomage actually here, right? Okay, so that's about this hierarchy over here. Very quick walkthrough, but I would suggest you maybe download the PDF and then take a look and then just get yourself familiar with the feature. So later on, when we talk about examples related to this hierarchy, it will be straightforward to you. Okay, so let's now go back to the slides, and now let's talk about inheritance hierarchy over here, and let's define some terms that that's going to be critical for us to define, many of the formal rules that we're going to present later. So we want to define, let's start with about the notion of type. A type or data type denotes a set of runtime values. For example, if you say my variable I is of type integer, so we are really saying I at the runtime can be a member of a set of 32 bits integer values, right? What about reference type? If I declare, for example, my variable P of type person, so that means P is an address that is a member of a set of possible addresses or memory locations for person objects. So you can think about a type is simply denotes a set of runtime values. Every class can be used as a type, so the set of runtime objects or the addresses for those objects to be more precise, because every reference variable only stores the reference, not really the entire objects. Okay, use of inheritance creates a hierarchy of classes. So that's something that's not just unique to iPhone, but for any OOP you're using, you always form a inheritance hierarchy always. So what would be the top? So implicitly, the root of the hierarchy is the any class. So this any class is analogous to the object class in Java. So implicitly, every class that you define in your iPhone projects, they implicitly inherits from the any class. So what are the typical features in the any class? Okay, let's talk about it quickly. So let me just talk about it, just sketch very quickly. So the default, the top hierarchy class is called any. Okay, it's effective class. Okay, it's called any, so it's analogous to the object class in Java. The typical features you have are, so it's equal. And also you got out. The out feature here is like the toString method in Java. And also the is equal is similar to the equals method in Java. Okay, similar concept over here. Okay, just want to make sure you understand. And implicitly, if you define any class, for example, person, in that case, implicitly, it will inherit from the any class. Okay, and then if you really want to maybe redefine or override the behavior for maybe is equal, you have to explicitly say inherits any, and then redefine is equal. Okay, so these are all the keywords that you learned previously, and then over here you have to redeclare the is equal with the compatible signature over here. Okay, of course that returns a boolean. Okay, so that's syntactically what you have to do in order to redefine any inherited feature from any class. So the inheritance from the any class is implicit. So that's the main point I'm trying to make. So this inheritance relation here is simply just implicit. Okay, let's go back to the slides. Okay, so each inherits declaration corresponds to an upward arrow. Okay, that's quite obvious. You can see over here, it's from the child class to the parent class over here. Okay, and then the inherits relationship is transitive. So when A inherits B and B inherits C, we say that A indirectly inherits C. Okay, that one is very easy to illustrate. For example, let's talk about a general inheritance hierarchy tree over here. Let's say A is somewhere in the tree. Okay, so now let's illustrate the first point. If we say A inherits from B, right, you can see the direction of the arrow, and also B inherits from C. We can say that because there's a path going from A to C, so we can say implicitly A inherits from C, implicitly. Okay, that's something I want to mention quickly. Okay, let's go to the next point. Every class implicitly inherits any class, right? That's quite obvious, right? Okay, so now, for example, in this particular inheritance hierarchy, A inherits from B, B inherits from C, and all the way to maybe some class over here, for example, Z. Okay, and then Z also implicitly inherits from any. So that's why we can say A also implicitly inherits from any. Or we can simply think about every class simply inherits from any implicitly. Either way is okay. Okay, so now let's define two very important terms in order for us to refer to the rules later. So ancestor versus descendants. You can think about ancestor is a more general concept for parents, and descendants is a generalized concept for child. Okay, so what about ancestor classes? So the ancestor classes of a class A are, number one, A itself. So remember, when we talk about ancestor, we always include the class itself. A itself and all the classes that A directly or indirectly inherits. Okay, let's take a look. So in this case, what would be the ancestors for A? Okay, let me just erase B and C just to avoid confusion over here. What will be the ancestor? Let's use ancestor, let's use green. Okay, first of all, it will be A itself, and also all the classes that A either directly inherits or indirectly inherits. In that case, it will be all the basically along the path all the way to the root. You actually got similar concept about figuring out the ancestor path in your previous data structure course, so there should be no surprise over here. So you can think about this part over here is the ancestor. Okay, so let's now first of all think about ancestor. So this part over here, all the green ones are the ancestors. Okay, let's go back to talk about more. A inherits all the features from its ancestor classes, and therefore A's instances have a wider range of expected usages, attributes, queries, and commands than instances of its ancestor classes. So what does it really mean? So now thinking this way. So think about, let me just illustrate it symbolically. Let's say if I got feature F1 over here, defined in this top class over here. So that means for sure F1 will be inherited to this class over here, and this class may also define F2 as a new feature. So now when we come to this class over here, for sure, number one, F1 and F2 will definitely be inherited. Let's say we also got F3 as a new feature. So now we come to A. So in that case, what can we expect from A? Well, number one, we can expect all the accumulated features from its ancestor classes along the ancestor class path. In that case, we can definitely get F1, F2, F3. You can think about all these features are inherited from the ancestors of A, right? And of course, ancestor including itself. But now for A over here, we can also define some new features. In that case, I can say F4 and also F5 and etc. So these are the new features. So now thinking this way, whenever we talk about expectation, so the expectation for this particular class is only F1, but this one here is definitely wider. So what's the new feature that we can expect? F2. And also this particular class also has a wider expectation for this class over here. So what's really more? Well, F3. And then for A over here, we also got a wider expectation compared with its parents over here. In that case, what will be the new one? Well, in that case, F4 and F5. Right? You can see the lower you are in the inheritance hierarchy, the wider expectation you can have for your classes. Okay. Let me just do one more illustration for you. Let's say A here, B here, C here. Let me just call it Z over here. Okay. So now think about the expectation. If you start with the expectation for Z, that one there is simply just F1. So this is the expectation set. Okay. Expectation set. Let's try another one. So that's for Z. What about for C? In C, it's strictly larger over here. In that case, what's the expectation set for C? In that case, not only F1, but also F2. Okay, and then let's try another one. What about the expectation set for B? So that will again be strictly larger over here. So now the expectation set for B. So what would it be? Not only that we got F1, F2, but also we got F3. Okay, finally, we have the expectation set for A. It's even wider, right? You can think about it's more like a superset. So now for expectation set for A. So now for A, not only that we got F1, F2, F3 from all its ancestors, also we got F4 and F5. F4 and F5. So now you can see from this subset diagram here very clearly, there are certain features that's the expectation for A, but not the expectation for any of its ancestor. On the other hand, any expectation that's actually any expectation of A's ancestor, for example Z, C, and B, they are definitely the expectation for A as well. Okay, of course, ancestor again. So the if we want to say strictly what's the ancestor, that should be including A. But sometimes when I say ancestor, I might be informally referring to maybe A's parents' ancestor. In that case, I'm really talking about these strict ancestor. Okay, I'll try to be more explicit if necessary. Okay, hopefully this makes sense. Just about the lower you are in the inheritance hierarchy, the wider the expectation is. Guys, this is a very important concept to realize. Okay, let's go back. And then the next one, the descendant classes. Okay, descendants as opposed to ancestor is a different concept. What about descendants over here? So now, if you think about descendant, let's see the definition. Okay, descendant classes of A will be A itself. So now you can think about A is both its ancestor and descendants at the same time. So you'll be A itself, and also all the classes that directly or indirectly inherit from A. So it's basically, think about, let me just try to use a different color here. Think about, it will be number one, A itself, and also all the classes that directly inherit from A. So there'll be these two, for example, and also all the classes that indirectly inherit from A. So that'll be the par. So now if I try to draw this over here, you can think about this would be, so this set of classes would be the descendants of A. So now, what about in terms of the expectation? Since we know every feature in A, for example, F1, F2, F3, that are accumulated from the ancestor, and also F4 and F5, these 5 features will all be inherited to this class, and all the classes. In addition to it, every class that's lower than A, they might define some new features, which means any class that's strictly lower than A, meaning it's a child's descendants. In that case, they will guarantee to have a strictly wider expectation, right? You can see the expectation concept is so important. All right. Okay, and then you can see the code defining A is inherited to all its descendant classes, meaning that all the strict descendants of A, so they definitely have strictly wider expectation. All right, so now let's talk a little bit more about, let's revisit the idea about inheritance accumulates code for reuse that we spoke about previously. So the lower a class is in the type hierarchy, the more code it accumulates from its ancestor classes. That's exactly what we just said. So a descendant class inherits all the code from its ancestor classes, and also it may declare new attributes, it may declare new queries or commands, the routines, or it may redefine the inherited queries or commands, right? That's something you know already. Just want to remind you. So what's the consequence of this? Let's discuss 2 consequences. Consequence number 1. When being used as a context object, instances of a class, descendant classes have a wider range of expected usages for attributes or routines. So what do I mean by that? Let's just use one example over here. We talk about context object, meaning that you're trying to make some feature call on the context objects. So let's say over here, let's just take 2 variables for example. Let's say I got object number 1 over here of type, let's say C. And also object number 2 of type A. So basically, I'm really saying for C, it's really talking about this particular class, right? And also, when I talk about A over here, it's really talking about this class over here, right? We got A and C, and we know that A is strictly lower in the hierarchy, so we can expect more from A because it accumulates all the code from its ancestor and also have some additional features. So now let's talk about that particular consequence. If now I say, let's say, assuming that we have already initialized both objects, let's say. So now, if I say here, if I say objects1, imagine that when you say dot, and then you're expecting the code completion to be available in the IDE, for example, iPhone Studio, versus if you got obj and then obj2, and then you say dot, and then you're expecting another list of features to be available. So now, let's say the list of features available for 1, let's call that list number 1. And then for object number 2, the list available feature will be, let's say, list number 2. So now, which list do you think will be larger? So that's basically about which expectation on the context objects will be wider. Okay, hopefully you realize because A over here is strictly lower in the inheritance hierarchy, so we know that A being the static type for object 2 means that object 2 over here can be expected to do more. Okay, so now over here, okay, let me be more precise. For object number 1 is simply just of static type C. So over here we just got F1 and also F2. Right, so these are the only two features we have, F1 and F2. What about A? Well, we got F1, F2, F3 inherited from the ancestors, and also F4, F5. So it's a strictly larger list. F2, F3, F4, and F5. So that's basically what I meant. By using an object as the context object, what would be the expectation on that particular variable? You have to see what the expectations are on its corresponding static types. So that's the first point. Okay. Let's go for the second consequence. When expecting an object of a particular class, we may substitute it with an object of any of its descendant classes. So this one, let me, again, I want to use two examples to show you. Let's still use this particular example. Let's still keep our two variables over here, object number 1 and also object number 2. Okay. Again, when we talk about substitution, let's say, when I say object number 1, right, it's substitutions in the context of OOP is about doing assignments. So it's really about, again, can we do object 1 is assigned to object 2? Or can we do object number 2 is assigned to object number 1? So this is really corresponding to the intuition regarding the polymorphism that we talked about previously, right? I think I don't think I'm gonna repeat the proof again to you. You can review the proof yourself. But now I can the way I explained it was exactly about expectation. So we know that this will be which one will be okay in this case. Well, I would say the best way to think about it is this: whenever you're doing this kind of assignments for substitutions, you should really think about static type. For object number 1, the static type is simply just C over here, and for object number 2. Okay, static type is C. And for the object number 2, the static type is A. Okay, let me just make the notes over here. So static type is A. And for object number 1, the static type is C. So now you want to think about whether or not, let's say the first one here, can you actually substitute object number 1 by object number 2? You can if the A over here can satisfy all the expectation that's imposed on C. Can you? Can you satisfy? The answer is yes, because A is strictly lower in the inheritance hierarchy. So of course, every feature that's actually that means A contains a strictly wider expectation. So for sure, A will everything that's expected from C, for example, F1 and F2, is definitely included in A. So this one here will be okay. What about the second one? The second one, we're going to argue a little bit similar to how we argued intuitively before. So now, can I substitute object number 2 by object number 1? So now it will be only possible if object number 1 is able to satisfy all the expectation that's imposed on object number 2. What? Meaning that it's static type A. For static type A, you will expect F1 and F2 for sure. F1 and F2, yes, can be satisfied by F1 and F2 in C. However, what about others? F3, F4, and F5, so these cannot be satisfied by C. Okay, so now over here, so this should be not valid. This is not a valid substitution. Because, for example, expectation on A, expectation on A, more precisely, F3, F4, and F5. F3, F4, and also F5 cannot negative be fulfilled by the right hand side C. So this is already, I'm already basically explaining to you the rule for substitution that we're going to cover in the next video. But I think in this context over here, it's really important for you to see. Whenever you're thinking about assignments over here, there is a corresponding inheritance hierarchy that you should be considering. And then whenever you want to substitute the left-hand side by the right-hand side, think about if the right-hand side is static type, can really fulfill the expectation that's imposed on the static type of the left-hand side. So that's always the rule you want to think about. Okay, again, it's all about expectation. Let me go back to the slides here. I think there's another example here. It's simply just using the simplified example that we've been using. Let's just talk about it quickly anyway. When expecting a student object substituted with either a resident student or a non-resident student objects will be okay. So what do I mean by that? Okay, very quickly. So now let's say we go back to this students hierarchy over here. So now if we try this, similar, you know, just almost like a repetition, but I think from a slightly different angle. So if I say S is of type students, and also we got RS is of, let me use NRS. It's a non-resident students. So now we know that statically the expectation on S, okay, students, the expectation would be basically name, courses, register, and tuition. So name, courses, register, and also tuition. So these are the expectation. On the other hand, what about the NRS? Its static type is now NRS, right? Because NRS is strictly lower in the hierarchy, so we can expect wider, we can have imposed wider expectation on non-resident students. So now in this case, what would that be? It would be whatever that's inherited from its parent class, students, so that'd be name, courses, register, tuition. In addition to this, also discount rate and also set discount rate. Discount rate and also set discount rate. So now when we talk about substitution, so there are two possible substitutions, but we got to decide which one is valid. When we say S is assigned to NRS, this would be valid because the expectation of NRS on the right hand side over here, let me write it down. So you can think about the expectation is more like a set. The expectation of the NRS, which is this set particularly. So this set over here is actually going to be larger than, strictly larger than, or equal to the expectation of the left-hand side. So let me just use the consistent color over here. So that one is green. So the expectation of the S. So since this set is strictly larger than that, well, actually, so I can even say it's a superset. Okay. So now in this case, you got this particular set is strictly larger than this set over here because we got at least as many over here. So we can definitely support all the expectation from S. So this is a valid one. Okay, it pretty much corresponds to the intuition that we talk about. On the other hand, if you try to do, let's say NRS is assigned to S. For this substitution to be valid, the following subset relation must hold. Meaning that over here on the right hand side, on the left hand side, over here, so we talk about NRS. So its expectation must be covered by those expectation of the right hand side, which is S, right? So now it should be covered by, so when we say covered by, that means it should be, this one here should be at least as many, okay, so of S over here. So is that possible? Does this subset relation hold? The answer is that it does not hold. How do we prove it? We prove it by showing one counterexample. So you can see over here, one counterexample will be part of the expectation for NRS will be dr. In this case, dr, you can see dr is a member of this set over here. However, if the substitution was successful, in that case, this one dr would not be able to be covered by the expectation of S. You can see from this set over here, there's simply the dr is simply not there, so it will crash at the runtime. So that's why this should not compile at the compile time. So this one simply just corresponds to what we said previously about the intuition of polymorphism. Okay, so that's enough about really about expectation and also how you can check them, you know, in the substitution like assignment context. Okay, so justification, if the subset relation actually holds, so that means the descendant class contains at least as many features as defined in its ancestor classes. So that's why over here, you can see the NRS, the static type over here is actually a descendant class of the static type of S, which is students. You can see NRS is a descendant class of students. So that means it has at least as many features that as in the students. But the other way around doesn't work, as we explained already. Okay, so finally, I would like to suggest two simple exercises for you. Let me just do a little bit just to get you started. Okay, I got two slides over here for you to just check your basic knowledge about ancestor descendants and also expected usage. Okay, let me show it to you. Okay, so now you can see that for the first row, what will be the ancestor for B, right? So that'll be easy. It will be a set of B itself and also A. So what about the expectation? Expectation for B will be Bn and also whatever that accumulates from its ancestor. So that would be Bn and also An. So what about the descendants? The descendants will be basically including B itself, right? So B over here, every other class that either directly or indirectly inherits B. So that'll be D, E, and I. D, E, and also I. Okay, let's also finish filling up. Also G and also we also got G. For example, G here. So what will be the ancestor? Okay, let's just write it down. So G and also it's G itself, C and also A. And also, what about expectation? So G will accumulate basically from its ancestor. So it will be AN, CM, and also GM. AN, CM, and also GM. I'm going to make a reservation together with you in just a moment once we finish. So what about for G? What would be its descendants? Well, in this case, itself for sure, and also whatever that's inherits from that. Well, in this case, just J. Okay, finally, let's also try what about for J over here. So J is over here. What about its ancestor? Well, will be J itself, and also G, C, and A. G, C, and A. What about descendants? Descendants over here, just J itself. What about expectation? It's going to be its own feature over here and everything that's accumulated from the inheritance from its ancestor. So it's going to be JM and also GM, also CM, and also AM. I want to make a very quick reservation for you, and then I'll leave you for the other exercise over here. If you consider B, G, and J, right? We got B here, we got G here, and we got J here. They kind of belongs to different branches, especially between B and G, and also between B and J. They do share some expectation in common. How do you tell? First of all, you can see from their ancestor. You can see, do they have a common ancestor? They do. Actually, A here, and A here, right? That's the kind of the lowest common ancestor they have. In which case, they're going to actually share expectation from A. So what will be the expectation from A? Well, simply AN, and also AN here. So that's the only common feature that's shared among the expectation of these three classes. Okay, but of course, if you go a little bit lower, let's say, what about between? Let's say between G and J, what would be their common ancestor? Well, in that case, it will simply be the G, right? Remember, G is also the ancestor of itself. So now if you look at G and J in a different color, so in that case, what will be the common ancestor for them? It will be the G, right? You can see the G over here. So that means their common expectation will also be whatever expectation it is from G. So that'd be GM, CM, and AM. So you can see GM, CM, and AM. So GM, CM, and AM. So I'm just trying to show you how you can really reason about the sets over here. So just about how you accumulate the expectation from common ancestors, if any. Okay, the final exercise I would like you to do, a simple one, is let's now switch to the inheritance hierarchy for our smartphone, which I ask you to maybe study a little bit. So now I would like you to really fill in the blanks over here for ancestor, expectation, and also descendants over here. Fill in the blanks, and then can you make similar observation as I did over here? For example, are there any common expectation between these two classes? For example, are there any common expectation between these two classes, for example? But how do you tell? Is it because they have a common ancestor? So that's a question for you. Okay, make a similar reservation over here and complete this simple exercise over here before you move on to the next video.